Somewhere around a distant red dwarf star, astronomers may have found a planet unlike anything our solar system ever prepared us for. It is too light, too hot, too strange, and its atmosphere may be filled with sulfur above a world of molten rock. Tonight, this quiet journey follows the new planet type that should not exist. If this kind of deep space mystery belongs on the channel, please like the video and subscribe for more. The search begins far from any single planet, in the wider field of stars that carry worlds around them. Over the last few decades, astronomy turns from a discipline that studies planets mostly within one solar system into one that surveys a crowded field of planetary systems spread through the Milky Way. Light from distant stars reveals slight dimmings, faint shifts, and repeated patterns. From those small signals, astronomers infer bodies that do not shine on their own. A planet passes in front of its star, a star wobbles under a planet's pull, a catalogue grows. In that catalogue, the first broad impression is variety. Some planets are larger than Jupiter and skim their stars in only a few days. Some are about the size of Earth. Some move through cooler, darker paths far from their suns. Even before any atmosphere or surface is considered, the planetary universe appears less orderly than the neat sequence once drawn from the solar system alone. That older sequence still matters. It provides the first language for comparison. In the solar system there are small rocky worlds, large gas giants, and ice-rich bodies farther out. Those categories arise from nearby study, and from a general picture of how planets form in a disk of gas and dust around a young star. Close to a star, heat strips away light materials more easily and favours dense rocky bodies. Farther out, colder conditions allow water and other volatile substances, meaning materials that are easily lost or moved by heat, to freeze and collect, helping large cores gather thick envelopes of gas. Yet the exoplanet census steadily shows that nature is not obliged to repeat the local pattern. The universe produces worlds that seem familiar only at first glance. Then a measurement of radius, mass, temperature, or chemistry begins to unsettle the label placed on them. Astronomers respond by building broader classes. The term super-Earth refers only to size and mass, not to habitability or likeness to Earth. A sub-Neptune is smaller than Neptune but still large enough to suggest a substantial envelope of gas or volatile material. A lava world is a planet so strongly heated that rock at the surface may melt. A Hycean world is a proposed class in which a planet might carry a deep ocean under a hydrogen-rich atmosphere. These names help map a growing terrain. They are practical, not final. Still, the deeper the surveys go, the more often a planet sits at the border between terms, or partly inside one class and partly outside another. The language of categories begins to stretch. Within that stretching language, astronomers sometimes use a sharper phrase. A planet is called impossible, not because it truly violates physical law, but because it resists expectations built from standard formation and evolution models. The word points to tension between observation and habit. A giant planet may circle so near an old swollen star that it seems unlikely to have survived. A large world may orbit a very small star that appears too meagre to have built it. A dense planet may seem too massive for the light atmosphere it still retains, or too light for the rocky composition once assumed. Impossible, in this scientific sense, means that a familiar story no longer fits cleanly. That tension is valuable. It keeps astronomy from confusing current models with permanent truth. A surprising world forces a closer look at formation histories, migration through a planetary system, atmospheric loss, and long-term heating. In many cases, the conflict softens with better data. In other cases, improved measurements deepen the problem. A class boundary has to move. A missing process has to be added. What once looks like an outlier begins to expose a blind spot in the way planets are sorted. The most revealing cases often arrive from a region that already appears troublesome in exoplanet surveys. This is the middle scale between Earth and Neptune, a size range that is common around other stars but absent in the solar system. Planets in this domain are neither easily grouped with the rocky inner worlds, nor simply treated as smaller versions of gas-rich outer planets. Their measured densities vary widely. Some appear dense and mostly rocky. Some appear puffier, suggesting gas or abundant volatile material. Some may have lost thick atmospheres over time. Some may never have formed them in the same way. This crowded region behaves like a place where several planetary histories overlap. From within that uncertain population, one world begins to stand apart. It does not earn attention because it is the biggest or the closest or the easiest to detect. It earns attention because multiple lines of evidence refuse to settle into an ordinary label. It lies in a size range where labels are already unstable, yet it pushes beyond even that looseness. Observations indicate a planet whose bulk properties are difficult to reconcile with a simple rocky body. At the same time, the world does not sit comfortably among water-rich or gas-dominated interpretations used for other planets of similar scale. Several features together suggest a state of matter and planetary history that standard categories do not describe well. This is why the phrase new planet type begins to enter the discussion. It does not arise from a wish to dramatize a discovery. It arises from restraint. Existing boxes are tested first. Rocky planet, water world, gas-rich small planet, heavily irradiated lava world. Each carries part of the picture, but none seems to contain the whole of it. Observations indicate one interpretation more strongly than others, yet some uncertainty remains because distant planets are inferred through light and models rather than directly touched. Even so, when measurements combine with atmospheric clues and interior calculations, a stronger pattern can emerge. A planet may not simply be odd. It may represent a physical state that has not previously been recognized as a distinct category. At this outermost stage, the world remains only a member of a vast planetary census, one data point against thousands. Yet even here, the significance is already clear. Planetary science depends on comparison. It learns by arranging worlds into families, then by noticing when a family resemblance breaks down. In that breakdown, a more precise picture of nature begins to form. The impossible planet is not a failure of classification alone. It is evidence that classification must remain open to forms of planet that standard expectations do not yet fully contain. Beyond the broad census of planets, the map begins to tighten around one especially crowded and confusing region. This is the middle ground between the smallest rocky worlds and the larger planets wrapped in thick outer layers of gas or volatile material. In the solar system, that middle ground appears almost empty. Earth and Venus sit below it in size, while Uranus and Neptune sit above it. Around other stars, however, this range is common. It may even be one of the most common outcomes of planet formation in the galaxy. That fact alone changes the sense of what is ordinary. A world type that seems unusual from the local view may be common in the wider Milky Way. Astronomers first identify this region by size. Many of these planets measure between about 1.5 and 4 Earth radii. That sounds like a simple bracket, but the physics inside it is not simple at all. A small change in radius may mean a large difference in composition. A planet only modestly larger than Earth may still be mostly rock and metal, with a dense interior and only a thin outer layer. Another planet of similar radius may hold enough gas, water-rich material, or lower density matter to make its bulk very different. Two worlds can look close in size and yet belong to different physical families. Mass helps, but mass does not solve the problem by itself. When astronomers combine mass and radius, they estimate density, and density offers a first clue to composition. A high density points toward rock and metal. A low density suggests substantial lighter material. Yet density is a blended property. It does not reveal a planet layer by layer. A world can achieve a similar average density in more than one way. It may have a rocky interior with a modest hydrogen-rich envelope. It may contain large amounts of water or other materials that remain fluid or superheated under pressure. It may have lost part of an atmosphere that was once much larger. The middle range becomes difficult not because the measurements are poor, but because nature allows several plausible structures to produce similar broad numbers. This difficulty leads to two of the most common labels in modern exoplanet science. One is super-Earth, the other is sub-Neptune. Neither name fully describes a planet's surface or climate. They're shorthand for a broad physical tendency. A super-Earth is generally understood as a planet larger or more massive than Earth, but still dominated by rock and metal. A sub-Neptune is smaller than Neptune but large enough and light enough to suggest a significant outer envelope of gas or volatile material. The trouble is that many planets fall near the boundary between those ideas. They do not clearly declare which structure they possess. As more planets are measured, a pattern emerges within this range. There appears to be a relative dip in the number of planets at certain intermediate sizes. Astronomers call this the radius valley, meaning a gap or thinning in the size distribution. One cluster of planets sits below the valley, often denser and more likely to be rocky. Another cluster sits above it, often puffier and more likely to carry thicker outer layers. This pattern suggests that small planets do not all follow one smooth path of growth. Instead, they may separate into different outcomes. Some lose primordial hydrogen and helium, some keep part of it, some may begin with different inventories of gas from the start. Several processes may help carve this valley. One is atmospheric escape driven by the host star. Young stars can be active and bright in high-energy radiation. That radiation heats upper atmospheres and can drive lighter gases into space, especially on planets that orbit close in and have lower gravity. Another possible process is internal heat loss. A young planet begins hot from its formation. As it cools, the energy flowing outward can help unbind a light atmosphere from above. This idea is often called core-powered mass loss, because the planet's own cooling interior contributes to stripping the outer layer. Observations support the view that both stellar radiation and internal heat matter, though their relative importance likely differs from system to system. Even with these ideas, the middle range remains unsettled. A planet above the radius valley is not automatically a small gas world in the familiar sense. The envelope may be thin in mass yet large in volume, because hydrogen and helium are light and expansive. A surprisingly small fraction of a planet's mass can still enlarge its measured radius. At the same time, some planets may contain substantial water-rich layers or other hot volatile materials beneath a thinner gaseous exterior. In such cases, the term sub-Neptune becomes more of a practical observational label than a precise description of what lies inside. Temperature complicates the picture further. Many middle-sized exoplanets orbit much closer to their stars than Mercury does to the Sun. Strong irradiation can transform chemistry, structure, and long-term evolution. A planet that might once have resembled a compact gas-rich world can be slowly reshaped by heat, and escape. A planet that appears rocky in bulk may still carry a remnant envelope or an unusual outer layer maintained under extreme conditions. There is no single middle planet recipe. There is a field of possibilities shaped by birth conditions, migration history, and the changing energy of the host star. This is why the region between super-Earths and sub-Neptunes becomes so important. It acts less like a neat category and more like a borderland. It is a place where planetary science tests how much can be inferred from mass, radius, and starlight alone. Each new well-measured planet in this zone helps define where rocky worlds end, where gas-rich worlds begin, and whether those are even the only two dominant outcomes. Observations indicate that some planets here are stripped cores, some are gas-bearing survivors, and some may belong to states of matter and heat balance that do not fit comfortably inside either label. In that sense, the crowded middle zone is not merely a classification problem. It's a record of planetary history written in bulk form. Size, density, and orbit preserve traces of formation, loss, and survival. The more closely astronomers study this region, the less it resembles a simple bridge between two known classes. It begins to look like a domain with its own internal diversity, where one planet may appear only slightly different from another while hiding a profoundly different structure. In this zone, the ordinary language of exoplanets starts to thin, and the need for finer distinctions becomes impossible to ignore. The wider region now narrows to one small planetary system, compact and closely ordered around a faint star known as L9859. In the great scale of the galaxy, it is not an enormous system and not a distant giant architecture of wide, cold orbits. It is a tight arrangement, with several planets circling near their star in a space that would fit well inside the inner part of the solar system. That compactness matters. It means the planets are seen not as isolated discoveries scattered across unrelated stars, but as neighbours sharing one origin environment, one central source of light, and one long history of mutual timing. A system like this offers an especially clear setting for comparison. Each world becomes easier to understand against the others that move nearby. Astronomers value such systems because planets formed around the same star are not random strangers. They begin in the same protoplanetary disk, meaning the rotating disk of gas and dust out of which planets grow. The disk may vary from place to place in temperature, density, and chemistry, yet its worlds still inherit a common background. They arise from the same broad reservoir of material and evolve under the same stellar influence. Differences between neighbouring planets are therefore especially informative. When one planet departs sharply from another in the same family, the contrast points towards specific physical processes rather than toward wholly unrelated origins. L98-59 belongs to a type of system now familiar in exoplanet studies. It is compact, with multiple small planets orbiting close in. These are not vast gas giants tracing broad outer circles. They are smaller worlds, packed into short orbits, each repeating its year in only a brief span of days. This layout is very different from the spacious architecture of the solar system, where the inner rocky planets are separated by wider gaps and the giant planets begin much farther out. In compact exoplanet systems, closeness is the rule. Several planets can sit within a distance from the star much smaller than the orbit of Mercury around the Sun. That arrangement has practical value for observation. When planets orbit close to a star, they pass in front of it more often from the perspective of Earth. If the alignment is favourable, each crossing produces a small dimming of starlight called a transit. Repeated transits allow astronomers to measure orbital periods with high precision. In a system with several transiting planets, the timing of those passages can also reveal the planets tugging on one another through gravity. Small deviations from perfectly regular intervals, known as transit timing variations, help estimate planetary masses. In this way, the system becomes not only visible, but dynamically readable. Its planets leave marks on the starlight and on each other. The known worlds around L9859 are therefore more than separate points in a catalogue. They form a measured ensemble. Their sizes differ, their densities differ, their likely compositions differ. Yet because they belong to one compact family, their contrast can be laid side by side with unusual clarity. One may appear denser and more strongly rocky, another may seem lighter for its size. One may receive somewhat less irradiation, another somewhat more. The system becomes a natural laboratory in which closely related planets display different outcomes under slightly different conditions. Planet D, the focus of this study, gains much of its significance from that setting. It is not merely unusual in a vacuum of context, it is unusual among siblings. When astronomers study its measurements, they do so with the surrounding planets always nearby in thought, because those neighbouring worlds help define what counts as ordinary within the same system. A strange property in a single planet system may be blamed on uncertain formation history or incomplete comparison. In a multi-planet system, a difference becomes more specific. Why does this one world occupy this particular place in the family while the others take different forms? That question sharpens the scientific value of the measurements even before any deeper layer of the planet is considered. The architecture of the system also hints at a history of migration and settling. Compact systems are often understood not as miniature copies of the solar system, but as outcomes of crowded inner formation, inward movement, or both. Young planets do not necessarily remain where they first grow. Interactions with the disk can shift them inward or outward. Later gravitational interactions can reshape spacing and orbital relationships. By the time the system reaches long-term stability, the planets may preserve only a partial memory of their earliest positions. Even so, the final arrangement still encodes information. Orbital periods, spacing, and dynamical calm suggest that the system has reached a durable configuration, one in which the planets continue their repeated passages without catastrophic disturbance. This matters because a planet is never only itself. It is a member of an orbital pattern, the energy it receives, the tides it may experience, the amount of material it once gathered, and the losses it later suffered are all tied in some measure to its place in that pattern. In L98-59 Planet D occupies a specific middle position within the known inner family. That placement gives it a role both comparative and physical. It sits neither as the innermost furnace of the system, nor as the most distant temperate edge among the known close-in planets. It belongs to an intermediate orbital environment that is still intensely warm by solar system standards, yet distinct from its nearest neighbours. Because of that middle placement, Planet D is especially useful when astronomers compare possible evolutionary tracks across the system. The planets do not differ only in size, they also differ in how much energy reaches them over time, and in how that energy may alter their outer layers. A compact family like this allows planetary science to ask not simply what a world is, but how similar beginnings can diverge within a small radial span around one star. The result is a quieter but deeper kind of discovery. The system itself frames the puzzle. The 98-59 is not just the home of an unusual planet. It is the structured local environment that makes the unusual nature of that planet legible at all. At the centre of this compact system sits a red dwarf star, small, cool, and faint beside the sun, yet entirely sufficient to organize several planetary worlds around it. In the galaxy, stars of this kind are common. They do not dominate the night sky to human sight, because each individual star is dim, but they are numerous in the Milky Way. Their abundance makes them important to planetary science. A large share of the known exoplanets orbit stars smaller than the Sun, and many of the best measured compact systems gather around this stellar type. The outer environment of L98-59 therefore begins with something modest in appearance, but powerful in consequence, a low-mass star whose size, light, and long lifetime shape the entire setting of its planets. A red dwarf is a main sequence star, meaning a star that spends most of its life steadily fusing hydrogen into helium in its core. That description also applies to the Sun, but the rate is different. A smaller star burns fuel more slowly. It shines less brightly. It releases less total energy each second. Its surface is cooler, so its light is shifted toward redder and infrared wavelengths, rather than the stronger visible output typical of a hotter star like the Sun. In broad physical terms, L98-59 belongs to that quieter stellar family. It is less massive, less luminous, and cooler than the Sun, yet it remains stable on timescales so long that they stretch far beyond the present age of the universe for many stars of its kind. That long life matters because a star is not only a lamp, it is the enduring energy source around which all planetary histories unfold. A large bright star spends its fuel more quickly and changes more dramatically over shorter spans of time. A red dwarf proceeds in a slower manner. It settles into a durable state and can remain there for immense periods. For planets, that means the outer energy environment may persist with remarkable continuity once the most active early phases pass. The star does not need to be large to govern its system thoroughly. Its gravity holds the planets in orbit, and its steady flow of radiation sets the background conditions under which their outer layers evolve. The light from a red dwarf is different from sunlight not only in amount but in character. Because the stellar surface is cooler, more of the emitted energy comes at longer wavelengths. Infrared radiation becomes more important. Visible light remains present, but the balance changes. A planet near such a star therefore receives a different spectral environment, meaning a different distribution of wavelengths than a planet orbiting a hotter star at an equivalent heating level. This difference influences how atmospheres absorb energy and how molecules respond to starlight. Even before any single planet is described, the nature of the star has already defined the kind of illumination available throughout the system. A small star also draws its planets inward if they are to receive substantial warmth. Since the star shines weakly compared with the Sun, a planet must orbit much closer to gather a similar energy flux, meaning the rate at which radiant energy arrives at the top of an atmosphere. This principle makes compact planetary systems around red dwarfs especially common in detection records. Planets close to a small star pass across it often and block a larger fraction of its light during transit. The star's small size helps the planets announce themselves. Thus, the same stellar modesty that lowers the total brightness also improves the visibility of planetary signals to distant observers. L98-59, like many red dwarfs, must also be understood through its activity. Small stars are often magnetically vigorous, especially when young. Magnetic activity includes flares, energetic bursts, and high-energy radiation from the stellar outer layers. Such behavior can strongly affect nearby planets by altering upper atmospheres and driving chemical change. Red dwarfs are known for this difficult youth. Even after they settle, they may still produce episodes of activity. The extent and timing vary from star to star, and careful observation is needed in each case. In general, however, a planet family around a red dwarf forms and matures in a setting that may be calmer in total brightness than the Sun's environment, yet more demanding in short energetic events, especially early on. This combination gives red dwarfs a double character in planetary science. On one side, they are steady, long-lived, and abundant, which makes them ideal anchors for the search for worlds over long cosmic times. On the other side, their compact scale and magnetic behavior can create demanding conditions close in. The system around L9859 belongs to that physical reality. Its planets do not circle a brilliant yellow star with wide habitable distances and gentle orbital spacing. They live under a smaller central body whose faintness requires nearness, and whose youth likely carries a more intense high-energy phase than its calm present appearance alone might suggest. The star also sets the timing of the whole system in a deeper sense. A low-mass star evolves slowly. Its brightness can change over long spans, but not with the rapid aging of more massive stars. Planetary outer layers are therefore shaped not by a brief intense lifetime followed by swift stellar transformation, but by prolonged exposure to a relatively stable central source after early adjustment. Any atmosphere, any volatile inventory, any surface state that depends on long-term irradiation must be interpreted against that slow stellar clock. The planets of L9859 inherit not only the star's gravity and light, but also its patience. Seen from afar, the system's star may appear almost understated. It is not visually grand in the way bright nearby stars can seem. Yet this understatement is one reason it is so scientifically useful. Its small size sharpens planetary transits. Its low luminosity compresses the system inward. Its spectral character alters the balance of heating and chemistry. Its longevity extends the stage on which planetary processes continue. The outer environment of the L9859 system is therefore not empty space alone. It is the continuing presence of a red dwarf whose scale is small, whose influence is comprehensive, and whose quiet appearance conceals the full authority of a star over everything that circles it. Around a small star, distance becomes the first great divider of planetary experience. In the L9859 system, that distance is measured on a compact scale. The planets move so near their star that their years pass with remarkable speed when compared with the slow circuit of Earth around the Sun. Planet D belongs to this tightly bound inner arrangement. Its path is short, its motion rapid, and its exposure to stellar energy persistent. Before any atmosphere, surface, or interior is considered, this orbit alone begins to define the world. It tells how often the planet completes a full circuit. It tells how much light and heat arrive from the star. It tells how little room exists between the planet and the energy source that governs it. In planetary science, an orbit is more than a path through space. It is a repeating energy schedule. Each circuit sets the cadence of dayless heating at the top of the planet's outer boundary. For a planet like Earth, that cadence unfolds over a year long enough to allow seasonal structure when axial tilt is present. For a planet very near a red dwarf, the circuit is compressed into only a handful of days. Planet D moves through its year on that compressed timescale. Its star is much fainter than the Sun, yet because the planet remains so close, the amount of incoming energy is still immense by the standards of the inner solar system. Nearness compensates for faintness. This is one of the central lessons of compact exoplanet systems. A star does not need to be bright in the solar sense to create a very hot planet. What matters is the balance between stellar luminosity and orbital distance. When distance becomes small enough, the radiation received at the planet rises sharply. The flow of stellar energy spreads outward through space and weakens with distance. So a modest shift inward can produce a strong increase in heating. In such a system, the difference between one neighbouring orbit and the next can mark a meaningful change in planetary conditions. Planet D occupies one such closely defined band of energy, neither at the most extreme inner edge of the known family nor far enough out to escape intense irradiation. Its orbital period is brief. That briefness is not merely a numerical curiosity. It shapes how the planet is observed and how it evolves. Frequent transits allow repeated measurements and strengthen confidence in the period itself. Each passage across the stellar disk returns on schedule, giving astronomers a precise clock. From that clock comes the orbital distance through Kepler's laws, which relate period and distance to the mass of the star. Once the distance is known, the stellar energy arriving at the planet can be estimated. In this way, the orbit becomes a bridge from observation to physical condition. A repeating dip in light becomes a measure of heat. Planet D therefore lives under what may be called constant irradiation. The phrase does not mean that every point on the planet necessarily receives equal light at every moment. It means that the world as an orbital body remains locked into a regime of continual strong stellar input over long time scales. The orbit is short and stable. The star is persistently present at close range. There is no long cold excursion into the outer darkness, no sweeping movement between distant extremes like those seen in some elongated cometary paths. The world stays near its star, and the star remains the dominant external force at every circuit. Because the orbit is so tight, gravitational effects from the star are also likely to matter in a second way. Over time, close-in planets are expected to experience tidal interactions, meaning gravitational stresses that act to reduce rotational irregularity and simplify the spin state. In many such systems, astronomers infer that a planet may become tidally locked or enter another strongly constrained rotation pattern. This possibility arises naturally from close proximity, though the exact spin state can depend on orbital shape, internal properties, and history. Observations indicate the orbit is compact enough that tidal influence should be taken seriously as part of the external environment. Even without specifying the final spin with absolute certainty, the closeness alone implies a powerful long-term gravitational relationship between star and planet. The orbit also defines the pace of any orbital forcing. If there are slight gravitational interactions with neighbouring planets, those influences repeat on short schedules because the whole system is compressed. Planet D is not wandering through a vast lonely orbit. It is part of a dense inner arrangement in which several worlds move with swift regularity. This does not mean the orbit is unstable. On the contrary, the system appears durably organized. Yet the compact structure makes clear that Planet D exists in a region where orbital architecture is tight, measured, and dynamically intimate. From the standpoint of heat, the most important consequence remains the simplest one. The top of the planet's environment receives far more stellar energy than Earth receives from the Sun. The host star is dimmer, but distance dominates the exchange. A world placed sufficiently near even a small star can reach temperatures at which familiar planetary assumptions begin to fail. Rocks that are solid on Earth may soften or melt. Volatile substances may be lost, altered, or redistributed. The orbit itself does not reveal those later consequences in detail, but it establishes the forcing that makes them possible. The planet lives where incoming radiation is not a secondary feature, but a primary fact. This is why orbit comes before chemistry, before clouds, before ground, and before the deeper unseen layers, it is the first boundary condition of the planet. Planet D circles in a path so close that its year is brief, its exposure strong, and its energy budget dominated by continuous stellar input. Its orbit is not a background detail added after the planet is described. It is the outer frame within which every later planetary property must be understood. Around L98-59 planet D traces a rapid circle under sustained irradiation, and in that rapid circle the first defining truth of the world is already present. It remains near its star, and the star does not let it cool. For a distant planet, the first outer layer is not gas or cloud or rock. It is information carried by light. Before any physical surface or atmosphere can be described, the planet must first become legible through a series of tiny changes in the light of its star. In the L98-59 system, planet D is known in this way. It does not appear in a direct image as a bright disk or a resolved globe. It is read indirectly through repeated signals that are precise enough to reveal a real world hidden inside them. This observational layer forms the first true entrance into the planet. The world is reached not by approach, but by interpretation. The most important signal begins with transit. A transit occurs when a planet crosses the face of its star from the line of sight of Earth. During that passage, the star grows slightly dimmer. The dimming is small, but it is regular. It repeats every time the planet completes one orbit. The depth of the dip shows how much of the stellar disk is blocked. And from that ratio, astronomers infer the planet's radius relative to the star. If the star is well characterized, the planetary size can then be estimated more directly. This is one reason a small star is so useful. A small planet blocks a larger fraction of a small stellar disk, making the signal easier to measure. In a compact system like L98-59 transit becomes even more powerful because the events happen often. A planet with a short orbital period passes in front of its star again and again, giving astronomers many opportunities to refine the timing and depth of the signal. Each transit adds another piece of evidence. Noise can be reduced. Patterns can be confirmed. The orbit becomes a clock. The planet does not speak loudly, but it repeats itself with enough discipline that its presence becomes unmistakable. The shape of the transit also carries information. A clean entry, deeper middle passage, and clean exit help confirm that the signal belongs to a planet crossing the stellar disk, rather than to some unrelated stellar variation. The precise timing of repeated transits may also reveal slight deviations from strict regularity. In a system with several closely packed planets, these deviations can arise because each world tugs gently on the others through gravity. Astronomers study these changes in schedule and use them to estimate planetary masses. This method is especially valuable for small planets around small stars, where the architecture of the whole system helps disclose the weight of each member. Mass and radius together produce one of the most important first clues about a planet. When both are known, astronomers can estimate average density. Density does not provide a direct map of the interior, but it gives a broad physical constraint. A planet with a high average density is unlikely to be dominated by light gases. A planet with a lower value may contain a significant amount of lighter material, whether in the form of gas, volatile compounds, or some hot expanded outer layer. In this way, the transit signal and the gravitational signal work together. One provides size. The other helps provide mass. From the combination comes the first bulk portrait of the world. Yet the observational layer does not stop there. When a planet transits, a very small portion of the starlight passes through the outer edge of the planet's atmosphere before reaching distant instruments. different molecules absorb different wavelengths of light. This means the atmosphere can leave a patterned fingerprint in the transmitted light. The method is called transmission spectroscopy. Though the basic idea is simple, the atmosphere is not fully opaque at all wavelengths. It filters the starlight in a selective way, and that filtering can reveal the presence of specific gases if the signal is strong enough and the instruments are sensitive enough. This is where modern observatories, especially the James Webb Space Telescope, become decisive. Webb is designed to collect extremely faint infrared signals with high precision. Infrared wavelengths are especially important for small hot planets around red dwarfs, because many molecules of interest leave clear absorption features there, and because the host star itself emits strongly in that part of the spectrum. By comparing the starlight during transit to the starlight when the planet is elsewhere in its orbit, astronomers can isolate subtle wavelength-dependent differences. Those differences do not produce a photograph, but they do produce a structured spectrum. That spectrum becomes a physical clue to the planet's outer layers. The achievement is delicate. The planet is tiny beside the star. The fraction of starlight passing through the atmospheric edge is smaller still. Instrument behavior must be calibrated. Stellar activity must be considered, since spots and changes on the star can mimic or distort the signal. Statistical methods are used to compare models with observations. More than one atmospheric explanation may fit the data to some degree. For this reason, astronomers speak carefully. Observations indicate a set of likely possibilities. They test whether one interpretation is favored more strongly than another. Confidence grows not from a single dramatic measurement, but from consistency across repeated observations and physically plausible models. In the case of Planet D, the observational layer becomes especially important because the world sits in a part of parameter space where classification is already uncertain. Size alone does not resolve the issue. Mass alone does not resolve it. Even density leaves room for more than one structure. Spectroscopy adds a crucial further dimension. It does not merely say how large or heavy the planet is. It begins to say what kind of material interacts with the incoming light above the planet's deeper body. The planet's outermost accessible layer thus becomes a measured interface between radiation and matter. Everything known at this stage remains indirect, but it is not vague. The orbit is timed, the transit is repeated, the radius is inferred, the mass is constrained, the spectrum is measured. Each result is partial, yet together they form the first readable shell of the planet. Before any detailed chemistry or thermal structure is examined, the world is already taking shape as a coherent object in data. Planet D enters science first as a sequence of dimmings, timings, and filtered wavelengths. Through those disciplined traces of light, a distant and otherwise invisible planet becomes available to thought. By the time the planet has been located in its system, tied to its star, and read through repeating transits, a more concentrated portrait begins to form from three linked measurements. These are size, mass, and density. They are not yet a map of atmosphere or a view of the ground. They do not show color, cloud, or texture. Even so, they are among the most powerful first constraints in planetary science, because together they define the body in bulk. They reveal how much matter the planet contains, how widely that matter is spread, and how tightly packed the planet is on average. For L98-59d, those three properties do not settle the planet into a familiar class. They do the opposite. They create the first direct contradiction. The radius is one of the clearest measurements. Observations indicate that L98-59d is about 1.63 times the radius of Earth. This places it in the crowded middle scale already known to resist simple labeling. It is clearly larger than Earth, yet far smaller than Neptune. At this size alone, several interpretations remain possible. A planet of roughly this radius might be mostly rocky, with only a modest outer layer. It might instead carry enough light material to expand its size well beyond that of a dense rocky body. Radius is therefore a strong measurement, but not a solitary answer. It marks the planet's place on the map without explaining what fills that place. Mass adds the second piece. For L98-59d, the best current estimate is about 1.64 times the mass of Earth. This is a striking result because the planet is noticeably larger than Earth, while having only a moderately greater mass. If radius grew in step with mass for a rocky body of Earth-like composition, the resulting density would remain within a comparatively familiar range. Here, the balance does not behave that way. The planet's size expands more than its mass. The matter is spread through a larger volume without a matching increase in total weight. The world is therefore light for its size. Density emerges from that mismatch. Average density is calculated by taking the planet's mass and dividing it over the volume implied by its radius. For L98-59d, the resulting value is about 2 2/10 grams per cubic centimetre. Earth, by comparison, has an average density of about 5.5 grams per cubic centimetre. This means L98-59d is much less dense than Earth, and far less dense than a simple rock and metal planet of similar scale would be expected to be. The contradiction becomes immediate. A planet in this size range, if built mainly like an enlarged Earth, should not come out so light. This is the first point at which ordinary classification begins to fail in a precise and measurable way. The planet is too large and too low in density for an uncomplicated rocky interpretation. Yet it also does not resemble a miniature gas giant in any ordinary sense. Its total size remains modest. Its mass is not large enough to suggest a broad, deep envelope like that of Neptune. The difficulty is not that the data are vague. The difficulty is that the data are clear enough to exclude the simplest option without pointing cleanly to one older alternative. L98-59d occupies a physical middle state that the broad labels do not handle well. Planetary scientists often compare such measurements against internal structure models. These models ask what combinations of rock, metal, water-rich material, and gases could produce the observed mass and radius. For a dense rocky world, the model gives one family of curves. For a planet with substantial lighter material, it gives another. L98-59d falls away from the pure rock and iron expectation. Its density is too low. That statement is not a matter of taste or metaphor. It follows directly from the measured bulk values. Something less dense than ordinary rock and metal must account for a significant portion of the planet's total volume, and perhaps also part of its mass budget. At this stage, the exact identity of that lighter contribution does not yet need to be specified in detail. The bulk properties alone already tell a strong story. They indicate that the planet cannot be treated as a simple terrestrial body scaled upward from Earth. It must either contain a large fraction of volatile material, meaning material more easily retained in fluid or gaseous form under planetary conditions, or possess an internal state that keeps a substantial portion of the planet expanded and less tightly packed than a solid rocky world. The contradiction is therefore not between observation and arithmetic. It is between observation and an older expectation of what a small hot planet should look like in bulk. This is what makes L98-59d especially important. Many exoplanets show one surprising property. This planet shows a coherent bulk pattern that demands reinterpretation. Its radius does not sit comfortably with its mass. Its mass does not produce a density appropriate for a dry rocky body. Its density sits low enough that some significant component of the world must differ from the usual picture of compact stone and metal. Bulk measurement, which often serves mainly as a first rough sorting tool, here becomes the beginning of a deeper revision. There is also a broader lesson in this. A planet does not become strange only when an exotic chemical signature appears. It can become strange much earlier, at the level of its most basic physical proportions. Size, mass, and density are often treated as introductory facts, but in L98-59d they already contain the seed of a new category. The world is not merely somewhat unusual. It is organized in bulk like something that should not fit the standard small planet menu. Observations indicate a body larger than Earth, only modestly heavier, and far too light on average to be built in the ordinary rocky way. By the end of this bulk view, the planet remains unseen in any direct visual sense. There is still no landscape, no horizon, no cloud deck, no visible surface. Yet the contradiction has become real. L98-59d is measured as a planet of about 1.63 Earth radii, about 1.64 Earth masses, and an average density around 2 2/10 grams per cubic centimetre. These are calm numbers, but they overturn a familiar assumption. They show that this world, even before any finer outer layer is examined, is not an enlarged Earth and not an easy small Neptune. In the simple language of planetary bulk, it has already become a planet that does not belong where older categories expect it to belong. Above every deeper layer of L98-59d, above any molten ground and above the heavier air below, lies the thinnest and most exposed part of the planet's atmosphere. This is the uppermost region that starlight first encounters as it grazes the planet during transit. It is also the region most directly available to distant measurement, because the outer edge of the atmosphere can leave a small but readable imprint on the star's light. For this reason, the top of the air becomes the first true atmospheric region to emerge from observation. It is not a full view of the planet's climate. It is a narrow outer shell, faintly visible because it stands between the star and the telescope. In many exoplanets, that shell is elusive. Clouds can hide it. Instrument limits can blur it. Stellar activity can confuse the signal. For L98-59d, however, the measurements point towards something chemically distinct. Observations indicate sulfur-bearing gases high in the atmosphere, with hydrogen sulfide especially important to the present interpretation. There is also evidence for sulfur dioxide in the upper atmospheric signal. These are not small decorative details added after the main picture is complete. They are central to why the planet no longer fits comfortably inside older classes. The top of the air is not neutral, simple, or easy to fold into a standard small planet model. It carries a chemical signature that immediately sets the world apart. Hydrogen sulfide is a molecule made of hydrogen and sulfur. On Earth it is known as a gas associated with volcanic settings, decaying organic matter, and certain oxygen-poor environments. On a distant planet, its presence does not carry the same local associations. It is simply an indicator of sulfur chemistry in the atmosphere. On L98-59d, it matters because it points toward a sulfur-rich outer environment rather than one dominated by the more familiar combinations often invoked for small exoplanets, such as water-rich steam atmospheres or more neutral hydrogen-helium envelopes with only minor heavier gases. The signal suggests that sulfur is not a trace curiosity. It is part of the planet's atmospheric identity. Sulfur dioxide deepens that identity. This gas is also sulfur-bearing, but it has different chemical properties and different spectral fingerprints. Its appearance in the upper atmosphere strengthens the view that sulfur chemistry shapes the outermost atmospheric region in a sustained way. The gases do not seem to point toward a single, isolated molecule appearing by accident. Instead, they suggest a family of sulfur compounds present where the planet's upper air can interact with incoming stellar radiation. The atmosphere begins to look less like a generic hot envelope and more like a specific chemical environment. This matters because the upper atmosphere is the part most exposed to loss, alteration, and detection. It is thin compared with the deeper layers below, but it is where molecules are struck first by the radiation coming from the host star. It is the place where light is filtered during transit. It is the region that most directly connects observation to atmospheric composition. If sulfur-bearing gases are visible there, then the outer edge of the planet is already unlike the outer edges expected for a simple rocky super-Earth or a straightforward water-rich world. The top of the air becomes a boundary of classification. It says that whatever lies below, the planet's exposed chemical face is unusual. The signal is especially striking because L98-59d is not a large gas giant. On a much bigger planet, a chemically rich atmosphere might be less surprising simply because a large envelope is already expected. Here the world is only modestly larger than Earth. Yet the outer atmosphere appears to carry a sulfur-rich signature that resists the standard picture of a mostly rocky planet with little more than a thin secondary atmosphere. The measurements do not support that simpler expectation. They indicate an upper atmospheric composition more substantial and chemically distinctive than such a picture would suggest. At the same time, the upper atmosphere must be described with care. Observation does not provide a direct sample of the air. It provides wavelength-dependent evidence that certain molecules are likely present. Models are used to test which combinations best explain the measured transmission spectrum. More than one interpretation can sometimes remain possible in principle. For this reason, planetary scientists do not claim total certainty for every atmospheric detail. What they can say with increasing confidence is that sulfur-bearing gases are strongly implicated in the upper atmosphere of 98-59d, and that this atmospheric character fits the broader case that the planet belongs to a new and unusual class. The outer atmosphere also has a physical importance beyond chemistry alone. It is the planet's first interface with space. It is where the star's energy begins to deposit itself. It is where the atmosphere can expand, thin, and respond to high-altitude heating. It is also where the difference between one world and another becomes visible to distant instruments. Two planets may have somewhat similar masses and radii, yet their upper atmospheres can reveal entirely different outer identities. In this case, the outer identity is unmistakably sulfur-rich. That phrase does not mean the atmosphere is made of sulfur alone. The upper air is still part of a broader atmospheric system that likely includes hydrogen as a major component, yet at the top of the air, what stands out in the observed signal is not a bland hydrogen background, but the presence of sulfur-bearing molecules that absorb light in recognizable ways. This is what gives the planet its unusual atmospheric profile. The upper region is chemically marked rather than chemically quiet. Seen from afar, L98-59d remains only a faint interruption in starlight. Yet within that interruption, the top of the air has become visible enough to alter the planet's scientific identity. The outermost atmospheric region appears to contain sulfur-bearing gases, including hydrogen sulfide, with sulfur dioxide also indicated high above the planet. These gases occupy the exposed edge of the atmosphere where starlight first passes and where the planet first declares what kind of world it may be, before the deeper air is entered, before heat trapping and circulation are considered. The upper atmosphere already presents the essential fact. L98-59d wears sulfur at the top of its air, and that outer signature is one reason it should not exist in so familiar a planetary category. In the upper atmosphere of L98-59d, sunlight does not merely pass through, it acts on the gas. This is the realm of photochemistry, meaning chemistry driven by light. At these heights, the air is thin enough and exposed enough that incoming stellar radiation can break molecular bonds, rearrange atoms, and create new compounds that would not remain in the same balance deeper down. The upper atmosphere is therefore not a quiet chemical shell resting passively above the planet. It is an active zone in which light and matter meet continuously. On L98-59d, this interaction appears to shape the sulfur-rich signature already seen at the top of the air. The host star is a red dwarf, cooler and dimmer than the Sun in total output, but still capable of sending ultraviolet radiation into the upper reaches of the atmosphere. Ultraviolet light carries enough energy to alter molecules directly. When such radiation strikes sulfur-bearing gases, it can split them apart or push them into new reaction pathways. A molecule that remains stable at one level of the atmosphere may become short-lived at another once the radiation field changes. In this way, the upper atmosphere differs chemically from the denser gas below, not only because pressure is lower, but because light itself becomes a stronger governing force. Hydrogen sulfide is especially important in this setting. It is one of the sulfur-bearing gases indicated by observation, and it is chemically vulnerable in the upper atmosphere. Under the action of ultraviolet radiation, hydrogen sulfide does not simply remain unchanged. It can be broken apart into smaller components, freeing sulfur to enter other reactions. Some of those reactions can ultimately help produce sulfur dioxide and related sulfur compounds. The exact balance depends on temperature, pressure, available hydrogen, and the wider chemical inventory of the atmosphere, but the broader picture is clear. The sulfur chemistry seen high in the atmosphere is not a frozen inheritance from below. It is being processed by light. Sulfur dioxide carries a particular significance in that process. On exoplanets, as in parts of the solar system, sulfur dioxide is often treated as a marker of photochemical activity because it can arise where sulfur-bearing gases are being reworked under irradiation. Its presence high in the atmosphere of L98-59d therefore suggests more than composition alone. It suggests transformation. The upper air appears to be a place where the original sulfur inventory is chemically reassembled into forms that survive, at least for a time, in the radiation-exposed outer layer. The atmosphere is not simply sulfur-rich, it is sulfur-rich in motion. This kind of chemically evolving atmosphere is described as being in disequilibrium. Chemical equilibrium is the state in which the composition settles into the balance expected for the local temperature and pressure if enough time passes without strong external disturbance. Disequilibrium means that some additional process keeps pushing the composition away from that settled balance. In the upper atmosphere of L98-59d, stellar radiation provides exactly such a process. Light breaks apart molecules faster than lower, quieter chemistry alone would predict. New molecules form. Old ones are depleted. The result is a layer whose composition reflects continual forcing from above. That distinction matters because disequilibrium gives astronomers a way to connect observation with process. A sulfur-bearing spectrum is informative. a sulfur-bearing spectrum that is best explained by ongoing photochemical conversion is more informative still. It means the upper atmosphere is not only composed of certain gases, but is actively maintained in a chemically restless state. The world begins to look less like a small planet carrying a static remnant atmosphere, and more like a planet whose outermost air is being continually rewritten by the star. The vertical structure of such chemistry is important even if the precise profile remains uncertain. The upper atmosphere is where ultraviolet photons arrive first and where mean free paths, meaning the average distances particles travel before colliding become longer than they are below. Under those conditions, reactions that are rare deeper down may become efficient enough to matter. Molecules broken by light do not immediately restore themselves to the same form. They enter a web of reactions whose products can differ substantially from the gases supplied from lower levels. This is why the top of the air can present one face to the telescope, even while the deeper atmosphere may be chemically distinct. For L98-59d, that distinction is central to the present interpretation. The sulfur compounds observed high in the atmosphere are consistent with models in which ultraviolet radiation from the host star drives chemical conversion in the upper air. The atmosphere therefore appears layered not only in pressure and temperature, but in chemical behavior. The outer region is defined by irradiation. It is a place where sulfur-bearing molecules are sorted by exposure, broken and reformed under steady stellar influence. The signal seen during transit is a glimpse of that outer chemical workshop. This helps explain why sulfur appears so prominently in the observed spectrum. The upper atmosphere is where molecules leave their clearest transmission signatures, and it is also where photochemistry can enhance or sustain specific compounds relative to a simpler unmixed state. A gas that is abundant below but invisible above may contribute little to the observed signal. A gas that is produced or maintained in the upper region can become disproportionately important in what distant instruments detect. In that sense, the top of the air is not a neutral sampling layer. It is an active filter shaped by radiation, and on L98-59d that filter appears to favor visible sulfur chemistry. There remains uncertainty in the finer details. The exact abundances of hydrogen sulfide and sulfur dioxide are still being refined. Additional observations are needed to determine how strongly each species is present and how the balance varies with altitude. The full reaction network may include other sulfur-bearing molecules not yet securely measured. Even so, the present picture is already coherent. The upper atmosphere receives ultraviolet light from the red dwarf star. That light drives chemical reactions. Those reactions help produce the sulfur-rich pattern inferred from the transit spectrum. Observations indicate an atmosphere whose topmost region is chemically processed, not chemically inert. The result is a world whose outermost air is shaped by light in a very direct way. At the top of the atmosphere, sulfur-bearing gases do not merely linger as leftovers from elsewhere in the planet. They participate in a continuing cycle of breakup and recombination under stellar radiation. The upper atmosphere is therefore the exposed laboratory of the planet, where the star leaves its imprint not only as heat, but as chemistry. On L98-59d, the top of the air is a sulfur-lit zone of disequilibrium, and through that changing zone the planet first reveals how unusual it truly is. Below the upper sulfur chemistry of L98-59d lies a denser and more insulating region of air, the deeper heat blanket of the planet. This layer is not the thin exposed edge that transit observations touch most directly. It is the heavier atmospheric body beneath. Where pressure rises, collisions between particles become more frequent, and radiation from the planet's own hot surface struggles to escape. In planetary science, A greenhouse atmosphere is one that lets much of the incoming stellar energy reach lower levels while slowing the loss of heat back to space. ONL 98-59d observations and models indicate that the atmosphere does exactly this in a very strong way. The lower air appears thick, hydrogen-rich, and efficient at trapping heat. Hydrogen is the lightest element, but a hydrogen-rich atmosphere need not be slight. Around a hot planet, even a relatively modest amount of hydrogen by mass can fill a large volume and produce an extensive gaseous layer. This happens because hydrogen expands readily under heat, so the atmosphere occupies more space for a given amount of matter than a heavier gas would. For L 98-59d, this helps explain how a planet of only moderate mass can still carry an atmosphere substantial enough to matter deeply for its thermal state. The lower atmosphere is interpreted as a broad insulating envelope. This envelope matters because the planet receives intense stellar irradiation from its close orbit, but the atmosphere determines what becomes of that energy after it arrives. Some incoming radiation is absorbed at altitude, some passes deeper down. The planet below then re-radiates energy upward at longer infrared wavelengths as hot material loses heat. In a thin atmosphere, much of that upward radiation might escape more efficiently. In a thick hydrogen-rich atmosphere, escape becomes harder. The lower gas absorbs, scatters, and reprocesses the outgoing thermal radiation. Heat is therefore held within the system rather than being shed freely to space. The result is a powerful greenhouse state. This does not require an atmosphere composed mainly of the same gases that dominate greenhouse warming on Earth. The mechanism is more general. Any sufficiently thick atmosphere with the right radiative properties can trap outgoing heat. On L 98-59d, hydrogen is thought to provide the bulk structure of the lower atmosphere, while sulfur-bearing gases contribute additional opacity and chemical complexity. Together they create a deep, warm envelope in which cooling is strongly limited. Pressure increases steadily with depth in such a layer. As pressure rises, gas becomes denser, and molecules collide so often that the atmosphere behaves less like a tenuous upper shell and more like a continuous heated medium. Radiation can still move through it, but less directly. Photons are repeatedly absorbed and re-emitted or scattered. In simple terms, heat has difficulty finding a clean route into space. The lower atmosphere therefore holds a great deal of thermal energy and keeps the planetary surface region intensely hot over geologic time. Models of L 98-59d indicate that this process is strong enough to maintain temperatures above about 1,500 degrees Celsius at the surface and lower atmospheric base. At such temperatures, familiar rocky materials do not remain as ordinary solid ground. The exact vertical temperature profile is still uncertain because it depends on atmospheric composition, mixing, and circulation. Even so, the broad conclusion is stable. The deeper atmosphere is hot enough and optically thick enough to act as a long-lived thermal blanket. It is part of the planet's persistent state. The hydrogen-rich character of the lower atmosphere is also significant for survival. Small hot planets close to active stars are often expected to lose light gases over time through atmospheric escape. L 98-59d appears to have retained enough hydrogen to remain enveloped despite that expectation. The current interpretation is that the planet's deeper volatile reservoir and long-term thermal structure helps sustain this atmosphere rather than allowing it to vanish completely. The lower air is therefore both a product of planetary history and an active participant in the planet's present condition. Sulfur-bearing gases remain part of this deeper layer as well, though the chemical behavior here differs from that of the highly irradiated upper atmosphere. In the lower atmosphere, pressure and temperature are greater, and direct photochemical processing is less dominant. Molecules are instead shaped more by thermal equilibrium tendencies, vertical mixing, and continual exchange with the hotter region below. Hydrogen sulfide is especially important in this picture. It contributes to the sulfur-rich identity of the atmosphere. But in the lower air, it also belongs to the heat-trapping mixture that strengthens the overall opacity of the envelope. The deeper atmosphere is therefore layered not only by altitude but by function. The upper atmosphere is the region of exposure and photochemical transformation. The lower atmosphere is the region of retention and insulation. It is where the planet's energy budget settles into a form that resists cooling. It is where incoming stellar energy, reprocessed outgoing heat, and the radiative properties of hydrogen-rich gas combine into a durable greenhouse structure. This makes the lower atmosphere one of the decisive reasons the planet cannot be understood as a simple rocky body with a thin secondary sky. There is still uncertainty in the exact mass of the atmosphere and in the detailed abundance of each gas at depth. Observations during transit are most sensitive to higher levels, not to the deepest part of the air. The lower atmosphere is therefore inferred through models that link the measured spectrum, the planet's low density, and its long-lived molten state. That inference is strong, but it remains a model-based reconstruction rather than a directly sampled profile. In this deeper region of air, the character of L98-59d becomes clearer. The planet is not merely sulfur-marked at the top, it is wrapped below in an atmosphere that holds heat with unusual persistence. Hydrogen gives the lower air breadth and volume. Sulfur-bearing gases add chemical weight and radiative effect. Pressure rises, infrared escape slows, and the whole atmospheric body acts as a blanket over the world beneath. The lower atmosphere of L98-59d is the warm, heavy envelope that keeps the planet from cooling into something more ordinary. At the base of the deep atmosphere, where the heavy hot air meets the body of the planet, L98-59d reaches a boundary that is not a boundary in the ordinary terrestrial sense. There is no stable crust waiting beneath the sky. There is no fixed plane of stone, no rigid volcanic field, no cooled shell stretched over a hotter interior. Instead, the outer face of the planet appears to be molten. The surface is not a hard platform beneath the atmosphere, but a glowing liquid interface, a place where gas presses down on melt, and melt releases material back into gas. This is the first solid-looking layer in the structure of a planet, yet on this world it is not solid at all. On Earth, the word surface usually implies firmness, even where ground is broken, fractured, or volcanic. It remains mostly a crust, meaning a cooled outer shell of rock that preserves shape over long spans. On L98-59d, that expectation fails. Models indicate temperatures at the atmospheric base high enough to keep silicate rock molten across the globe. Silicate rock is rock built largely from silicon and oxygen combined with other elements, and it makes up much of the rocky material familiar in terrestrial planets. At the conditions inferred for this world, such material does not settle into a continuous hardened exterior. It remains liquid at the top. This changes the meaning of landscape. A solid planet presents mountains, plains, basins, ridges, and impact scars, all features preserved because the outer shell can hold form. A molten surface cannot preserve that sort of memory in the same way. Its shape is softer, more mobile, and constantly responsive to heat and flow. Any local rise or depression exists within liquid motion rather than upon an immobile crust. The surface becomes less like terrain and more like a restless skin spread over a planetary body that has not cooled into ordinary topography. The heat that maintains this state comes from the combined effect of strong stellar irradiation and the overlying greenhouse atmosphere. The close orbit delivers large amounts of energy from the star, and the thick hydrogen-rich lower air slows the release of that energy back into space. The result is a surface region that remains above the melting point of common silicate materials. This does not describe a short-lived episode such as a recent impact or a passing volcanic outburst. It describes the enduring outer condition of the planet. The atmosphere does not lie above cooled ground waiting to crack. It lies above melt. Because of this, the contact between atmosphere and planet is unusual in a second way. On a world with solid rock, the ground and the air exchange heat and gas through limited pathways such as weathering, volcanism, evaporation, and chemical reaction at exposed minerals. On AL 98-59d, the whole outer face of the planet participates in exchange. The molten surface itself is the interface. It can release volatile material, meaning material that enters the atmosphere comparatively easily under heat, not through isolated vents alone, but across an immense exposed area. The atmosphere above is therefore not merely resting over the planet, it is in active contact with the liquid outer body. This liquid outer face is often described as a magma ocean, but at the surface the term ocean can mislead if it suggests water-like calm or familiar coastlines. The comparison is useful only in one sense. It conveys continuity. The molten layer is not scattered pools or local lava fields. It is global. Across the planet's exterior, the atmosphere meets a broad connected expanse of silicate melt. That continuity matters because it prevents the formation of large, stable, continental-style regions, and removes the sharp contrast between land and sea that shapes so many familiar worlds. Here there is only one exposed planetary material at the base of the sky, and it is molten rock. The absence of a crust also means the surface cannot insulate the deeper hot material in the way a solid lid would. On many rocky worlds, even intense internal heat remains partly hidden because a rigid shell separates interior dynamics from the atmosphere. On L98-59d, the uppermost melt is already part of that dynamic zone. Heat can move through convecting liquid material far more directly than through an old, thick crust. The surface is therefore not a cooled endpoint. It is a hot participating layer within the planet's ongoing thermal state. This molten exterior likely glows with heat rather than reflecting light in the manner of bright cloud or pale stone. Its radiative character is governed by temperature and by the optical properties of molten silicate material. Under the thick atmosphere above, the surface is not necessarily visible in direct ordinary light from afar, yet physically it remains a radiant boundary. Energy moves upward from it continuously into the lower atmosphere. The atmosphere in turn presses downward and returns part of that energy through greenhouse warming. The surface and the air are locked together in thermal exchange. Chemical exchange also belongs to this boundary. Sulfur-bearing gases detected in the atmosphere point toward an intimate connection between the molten surface and the air above it. Material dissolved in the melt can be released as gas when pressure, temperature, and composition allow. That release need not resemble discrete eruptions in the terrestrial sense. On a global molten surface, degassing can be widespread and persistent. The surface thus acts as a planetary breathing boundary, though not in any biological sense. Gas comes out of melt, enters the atmosphere, is processed aloft, and can remain coupled to the molten exterior over immense spans of time. There is uncertainty in the exact texture of this boundary. The surface may not be equally smooth everywhere. Temperature differences, circulation within the atmosphere, and motion within the melt could produce regional variation in viscosity, wave structure, or crust-like temporary films. Observations do not yet resolve such details. What is much clearer is the larger state. The planet does not appear to possess a stable solid crust across its exterior. Its surface is best understood as a long-lived molten interface under a thick atmosphere. This makes L98-59d very different from the ordinary image of a small rocky world. Even if its mass and radius place it near planets often compared with Earth, the comparison fails at the boundary where world meets sky. There is no ground in the usual sense. There is only a planetary exterior hot enough to remain liquid, broad enough to be global, and chemically active enough to feed the atmosphere above it. At the surface of L98-59d, the atmosphere does not end over rock. It ends over melt, and the planet's face remains perpetually unfixed. Beneath the molten surface of L98-59d, the planet does not immediately pass into solid rock. The liquid exterior continues downward into a deeper connected body of silicate melt, a true global magma ocean. This is not a scattered set of lava basins or a shallow planetary glaze. It is a continuous outer layer in which rock remains molten over immense areas, forming a planetary shell of liquid stone. The word ocean is useful here because it describes continuity and breadth. It does not imply water or a familiar shoreline. It describes a world whose outer body behaves as melt on a global scale. A magma ocean forms when temperatures remain high enough that silicate material stays liquid rather than freezing into a rigid crust. On some young planets, such oceans may exist only for a short early interval after formation or giant impacts. On L98-59d, the present interpretation is different. This ocean is not simply an ancient phase remembered in mineral traces. It appears to be a long-lived condition maintained by the planet's present environment. Strong stellar irradiation and a deep greenhouse atmosphere work together to keep the outer rocky layer from solidifying. The magma ocean is therefore not a brief aftermath. It is part of the planet's steady state. This distinction matters because a persistent magma ocean behaves differently from a temporary one. A short-lived molten episode may cool, separate minerals, and leave behind a crust that seals the planet from direct atmospheric contact. A lasting magma ocean does not take that final step. It remains mobile and exposed over geologic timescales. The outer part of the planet continues to convect, meaning hot material rises while cooler material sinks, carrying energy through the melt by movement rather than by conduction alone. This circulating motion prevents the ocean from becoming a stagnant outer shell. Convection in molten rock is slower and heavier than convection in air, yet on planetary scales it is effective. Heat deposited at the top by stellar forcing and held in by the atmosphere does not simply rest at the surface. It is shared through the upper molten region by the movement of the melt itself. Hotter parcels become more buoyant and rise. Slightly cooler parcels sink. The magma ocean therefore does not behave as a smooth static pond. It behaves as a churning planetary reservoir in which temperature and composition are continually redistributed. Because the ocean is global, this redistribution is not local in meaning. A volcanic province on Earth can exchange heat and gas with its surroundings, but it remains a limited feature on a mostly solid world. On L98-59d, the magma ocean is the surroundings. It is the dominant outer rock layer of the whole planet. That gives it enormous control over the thermal and chemical character of the world. The atmosphere above does not rest over isolated eruptions. It rests above a planet-wide molten reservoir that can absorb, store, and release energy continuously. The depth of this ocean remains uncertain. observations do not yet directly reveal how far downward the molten outer layer extends before conditions grade into a deeper silicate region of different behavior. Models indicate that the ocean is substantial, but they do not yet resolve a single exact boundary. Even so, the broad conclusion is robust. The molten layer is not a thin superficial film. It is deep enough to act as a structural part of the planet rather than a decorative outer skin. Within such an ocean, the chemistry of rock is transformed by being held in liquid form over long spans. Elements and compounds do not remain locked inside crystals as they would in cooler solid stone. They dissolve into the melt, move with it, and separate according to temperature, pressure, and chemical affinity. Sulfur is especially important in this setting. The atmospheric sulfur signature suggests that the magma ocean acts as a vast reservoir for sulfur-bearing material. The melt can store sulfur in dissolved form and then release part of it back toward the atmosphere through ongoing degassing. Degassing from a global magma ocean differs from the eruption-driven picture familiar from Earth. On a solid planet, gases are often released through vents, fissures, or explosive events tied to local pressure changes. In a planet-scale molten layer, volatile release can be far more broadly distributed. Wherever the conditions of pressure and composition allow, gases dissolved in the melt can escape upward into the overlying atmosphere. The whole ocean becomes a source region. This gives the atmosphere a continuing connection to the planetary body below. The magma ocean also acts as a thermal memory. Because it is deep and massive, it stores immense quantities of heat. Even if external forcing varies somewhat over time, the molten layer does not respond instantly in the manner of a thin surface sheet. Its scale gives it inertia. Heat enters, circulates, and is retained through the large volume of moving silicate material. This helps the planet remain in a durable molten state. It possesses a deep reservoir capable of sustaining the hot outer condition through time. Pressure within the magma ocean rises with depth, and rising pressure changes the behavior of the melt, viscosity, density, and the solubility of gases can all vary downward. The upper part of the ocean, closest to the atmosphere, may dega more readily. Deeper parts may hold volatile material more effectively in solution. Composition may become layered in places if certain minerals begin to separate or if circulation is not perfectly uniform. The details remain uncertain, but the main physical picture is clear. This is a structured liquid layer, not a simple homogeneous pool. Its presence also helps explain why the planet's bulk density is so low for a world of its size. A global magma ocean under a hydrogen-rich atmosphere contributes to an expanded, less compact planetary structure than a fully solid rocky shell would. The planet's outer body is not tightly packed into a cool, rigid form. It remains thermally swollen and compositionally unusual. Seen as a whole, this layer gives L98 to 59d much of its identity. Beneath the molten surface, the magma ocean extends as a connected planetary reservoir of liquid silicate rock. It convects, stores heat, dissolves volatile material, and feeds the air above. It is not a brief phase or a marginal feature. It is one of the defining bodies of the planet. On L98-59d, the outer rocky world has not frozen into crust. It remains a global ocean of melt, and in that persistent molten shell the planet finds its unusual form. Deeper beneath the global magma ocean of L98-59d, the planet enters a region that is still not solid in the ordinary sense. The molten outer reservoir does not end abruptly at a clean frozen boundary. Instead, the deeper silicate mantle appears to remain in a hot, mobile state over a vast fraction of the planet's interior. This is the part of the world where the distinction between ocean and mantle becomes less a difference between liquid and solid and more a difference in pressure, density, and style of motion. The upper magma ocean is the exposed outer melt layer in direct exchange with the atmosphere. The deeper mantle lies below it as a broader volume of molten or partially molten silicate material, hidden from direct observation but strongly implied by the planet's thermal and structural state. On a cooler rocky planet, the mantle is usually described as solid rock that flows only very slowly over immense spans of time. Earth offers that familiar example. Much of Earth's mantle is not liquid, even though it is hot. It behaves as a solid that can creep under pressure, allowing convection across geological ages without becoming a free global melt. L98-59d appears different. Models indicate that temperatures remain so high and the thermal structure is so strongly supported by stellar heating and atmospheric insulation that the silicate mantle does not settle into that mostly solid condition. Instead, much of the rocky interior is thought to remain molten or mushy, meaning partly liquid and partly crystalline, across a great depth. This deeper region is still built from silicates, the same broad family of rock-forming materials that dominate rocky planets. Yet under the conditions inside L98-59d, those materials do not take the ordinary form of rigid stone. Pressure rises downward, and that rising pressure changes the melting behavior of minerals. In some ranges, higher pressure can make complete melting harder. In others, composition and temperature can sustain melt across wide zones. The result is not expected to be a perfectly uniform liquid, extending unchanged all the way down. It is more likely a gradation of states, with highly molten regions above, denser and perhaps more crystal-rich molten regions below, and motion shaped by the changing balance between temperature and compression. The important point is that this region still belongs to the planet's active hot body rather than to a quiet frozen interior. Most of the world's volume appears to be dominated by this deep silicate domain. The planet is not a small metallic center wrapped in a thin skin of lava and gas. It is better understood as a body whose interior is largely composed of hot, mobile, rocky material extending inward through much of its radius. This helps explain why the planet's structure differs so greatly from the compact architecture expected of a cooled terrestrial world. In the deeper silicate mantle, motion continues, but it is not the same as motion in the upper magma ocean. Near the top, heat exchange with the atmosphere and the exposed molten surface keep the outer layer directly engaged with stellar forcing. Deeper down, the mantle is governed more by internal gradients of temperature and density. Hotter material still tends to rise, and denser, cooler material tends to sink, but the flow becomes slower, heavier, and more strongly constrained by pressure. The melt may circulate through broad overturning patterns rather than through surface-like churning. This is a planetary interior in motion, not a still reservoir. That motion is central to the long-term durability of the molten state. A deep silicate mantle that can transport heat by movement remains dynamically connected to the outer layers. Energy does not simply collect at the surface and stop there. It is distributed through the interior, and the interior in turn contributes to the thermal condition of the planet above. The mantle acts as both a storehouse and a transport medium for heat. Because so much of the planet's body may be in this state, the entire world possesses a strong thermal inertia, meaning a resistance to rapid cooling. The planet does not solidify easily because its hot silicate interior is both deep and extensive. Composition within this mantle is also likely to vary with depth. Even if the material is broadly silicate, different minerals become stable under different temperatures and pressures. Some crystals may form within melt and then sink or remain suspended depending on their density and abundance. Other portions may stay more completely molten. This can produce a layered or gradational interior rather than a single homogeneous mass. The details remain uncertain because no telescope can directly image these interior zones. Still, the general physical picture is consistent with a deep mantle in which molten silicate material dominates and internal differentiation, meaning the sorting of material by density and chemistry continues within a largely hot and mobile framework. This deep mantle is also one reason the planet does not behave like an overgrown Earth. Earth's modern internal structure includes a relatively thin crust, a mostly solid mantle, and a metallic core. L98-59d appears to depart from that pattern in a major way. The crust is absent as a stable global layer. The outer rocky shell is molten. Below it, the mantle is not mostly solid but remains in a much hotter and more liquid condition. The result is a planet whose interior is expanded and dynamically different from the familiar terrestrial model. The deeper mantle is therefore not merely another layer below the magma ocean. It is the dominant rocky body of the world. Its physical properties are likely shaped by extreme temperature, combined with substantial dissolved material. In molten silicate systems, viscosity, density, and heat capacity all depend on composition as well as pressure. A mantle richer in volatile components or chemically unusual in its rocky makeup may remain less like the mantles known from the solar system and more like a distinct exoplanetary material state. This remains an area of active modelling rather than settled direct measurement, but it reinforces the sense that the planet's interior is not simply hotter than Earth's. It may also be compositionally unfamiliar in ways that matter to its large-scale behaviour. The sheer extent of this region is striking. Current interpretations suggest that molten and partially molten silicate material may occupy most of the planet's radius, leaving only a relatively smaller central core beneath. In that case, the deeper mantle is not a secondary feature tucked under a surface ocean of melt. It is the main body of the planet itself. The world is, in a structural sense, a vast mass of hot, rocky fluidity under pressure. The atmosphere and magma ocean are the outer expression of a much larger molten architecture within. There is still uncertainty in where the deepest fully molten zones give way to more crystal-rich material, and in how sharply one sublayer transitions into another. The present data cannot specify every internal boundary. What they do support is a coherent inward picture. Beneath the exposed magma ocean lies a deep silicate mantle that remains hot, mobile, and largely unsolidified across most of the planet's interior. This is rock under immense pressure, but not the quiet locked rock of a cooled terrestrial planet. It is a mantle still participating in the molten life of the world, on L98-59d. The deeper interior is not yet a realm of still stone. It remains a vast concealed body of liquid and near-liquid rock, carrying the planet's heat through its greatest hidden volume. Deep within the molten body of L98-59d, sulfur does not appear only as an atmospheric gas. It is stored below, dissolved and retained inside the hot silicate interior. This hidden sulfur reservoir is one of the most important features of the planet, because it helps connect the strange chemistry of the atmosphere to the deeper structure of the world itself. The sulfur seen high in the air is not best understood as a thin accidental veneer. It is more likely the exposed expression of a much larger inventory held inside the molten planet over immense spans of time. On a cooler rocky world, volatile elements and compounds can be partitioned, meaning distributed, among minerals, melts, gases, and metallic phases in ways that change as the planet cools. Sulfur is especially sensitive to these conditions. It can dissolve in molten rock. It can escape into gas. It can also be drawn into metallic material under some circumstances. On L98-59d, the dominant fact is that the planet stays hot enough for much of the rocky body to remain molten or near molten. This gives sulfur a very different long-term environment from the one found in a solidifying terrestrial planet. Instead of being locked away early in crustal minerals or lost quickly through one phase of volcanic outgassing, sulfur may remain mobile and exchangeable within a vast interior reservoir. The magma ocean and the deeper silicate mantle together provide that reservoir. In molten silicate material, sulfur can remain dissolved over a wide range of pressures and temperatures, though the exact amount depends on the composition of the melt and the redox state, meaning the balance between chemically reducing and oxidizing conditions. That balance influences which sulfur-bearing species are stable and how readily sulfur moves between melt and gas. The details of those deep conditions on L98-59d are still being modelled rather than directly measured, but the broader picture is strong. The planet's interior is hot enough, deep enough, and molten enough to store very large amounts of sulfur for geologic timescales. This storage changes the meaning of the atmosphere above. If sulfur were present only in a shallow outer layer, the atmospheric signature might be brief or easily exhausted. A small, isolated supply would become chemically altered by starlight, and eventually diminish unless renewed. The observations instead support a world where sulfur-bearing gases can persist, because the supply below is enormous. The atmosphere is therefore not best pictured as a sealed envelope with a fixed initial composition. It is part of a continuing exchange system, fed from beneath by a deep interior that still contains abundant sulfur. In such a system, degassing becomes a long planetary process rather than a one-time event. Sulfur dissolved in the melt can move upward through convection and approach lower pressure regions near the top of the magma ocean. As pressure drops and local conditions change, some of that sulfur leaves the melt and enters the atmosphere in gaseous form. This release does not need to occur through isolated volcanoes alone. On a planet with a global molten exterior, degassing can be spread across broad regions of the atmosphere melt boundary. The whole upper interior participates in slow continuous transfer. Once sulfur enters the atmosphere, it becomes part of the chemistry already seen in the upper layers. Hydrogen sulfide can form and persist in lower regions before being altered at higher altitude by radiation from the star. Sulfur dioxide can arise as part of that atmospheric processing. Yet the important inward fact is that the atmosphere does not generate sulfur from nothing. It inherits sulfur from the molten body below. The deep interior therefore acts not only as a source of heat, but also as a chemical reservoir that sustains the planet's visible atmospheric identity. The size of that reservoir may be one reason the planet remains so unusual. In more familiar planetary models, a small hot world close to its star might be expected either to lose much of its atmosphere or to settle into a chemically simpler state over time. L98-59d appears to resist that path. Its sulfur-rich atmosphere and long-lived molten condition suggest a deeper storehouse capable of renewing and stabilizing the gases above. This does not imply perfect constancy. The precise atmospheric composition likely changes through time. Rates of degassing, photochemical conversion, and escape may vary. Still, the existence of a deep sulfur inventory allows the system to endure rather than fade quickly into a thinner and less distinctive state. Sulfur hidden at depth also affects the internal material properties of the planet. Dissolved sulfur can influence the melting behavior of silicates, the speciation of gases, and the chemical partitioning between different interior regions. A sulfur-rich molten interior may therefore behave differently from the rocky interiors familiar in the solar system. It may retain volatile material more effectively in some zones, release it more efficiently in others, and support an atmospheric chemistry that reflects deep planetary composition more directly than on a world sealed beneath crust. In this way, sulfur is not merely an atmospheric ingredient. It is part of the planet's structural character. Because the interior is largely molten, the sulfur reservoir is not static. Convection moves material over time. The upper magma ocean and deeper silicate mantle continually redistribute heat and composition. Sulfur dissolved at one depth may, over long intervals, be carried upward or downward according to changing pressure, temperature, and local chemistry. This makes the planet's sulfur budget dynamic rather than layered into rigid permanent compartments. There may still be gradients in concentration, and some regions may hold sulfur more effectively than others, but the overall interior remains a circulating system. The long retention of sulfur also helps distinguish L98-59d from a purely evaporating remnant. It is not simply a stripped rocky core with a few leftover gases clinging to it. Instead, it appears to be a world whose molten interior actively preserves and supplies volatile material even after billions of years under intense irradiation. That endurance is one reason the planet challenges standard expectations. It suggests that some small close-in planets can remain chemically rich and thermally inflated far longer than simpler models once implied. There remains uncertainty in the exact total amount of sulfur stored inside the planet, and in the detailed chemical form that sulfur takes at the greatest depths. Different interior models allow somewhat different distributions. The redox state is not directly known. The pressure-dependent partitioning between melt, gas, and any denser interior component is still being refined. Even so, the central interpretation is consistent across the current picture. 98-59d holds a vast sulfur inventory in its molten interior, and that inventory is large enough to matter on planetary scales. By this stage, the atmosphere above is no longer best seen as a detached layer, and the magma ocean below no longer as a heat source alone. They are linked by sulfur. What rises into the air begins deep in the planet's molten body, dissolved and stored across a broad interior reservoir. The strange sulfur chemistry visible high in the atmosphere is therefore rooted in the hidden depths of the world. L98-59d keeps sulfur below as well as above, and in that concealed store the planet preserves one of the clearest signs that it belongs to a class unlike the ordinary rocky and gas-rich worlds already known. At the deepest inferred level of L98-59d, the planet may finally gather into something more compact than the vast molten silicate body above it. This is the region most likely to contain a metallic core, a central concentration of denser material formed as heavy elements sink inward during planetary differentiation. On many rocky planets, such a core is treated as a defining internal anchor, distinct from the mantle that surrounds it. On L98-59d, the core is still expected in principle, but it appears to be relatively small compared with the enormous depth of molten silicate material above. This does not remove the core from the planet's structure. It changes its proportion and its clarity. A metallic core usually forms because iron and other dense metal-rich components separate from lighter, silicate material during the hot early stages of planetary evolution. Gravity does the sorting. The denser material tends to sink toward the center, while the lighter rocky material remains above. This broad process is thought to operate widely in rocky worlds, including Earth, Mercury, Venus, and Mars. 98-59d almost certainly begins with the same physical tendency. its present state is so hot that its early differentiation is unlikely to have been prevented. Instead, the deeper question is not whether some denser central region exists, but how large, how compositionally distinct, and how sharply bounded that region remains after billions of years in a long-lived molten state. Current interpretations suggest that the metallic core, if present as a clearly separate inner body, occupies a much smaller fraction of the planet's radius than the surrounding molten silicate envelope. The magma ocean and the deeper silicate mantle together appear to dominate most of the interior. This means the central core does not set the visible character of the planet in the way Earth's core supports a familiar layered terrestrial model beneath a mostly solid mantle and crust. On L98-59d, the core lies buried under a far thicker zone of hot silicate material, and its contribution to the total radius is modest. That modest scale matters because the core becomes less architecturally dominant in a world whose outer and middle regions remain molten across such great depth. The central metallic region may still hold much of the planet's densest material, but the overall bulk structure is governed more by the expansive molten silicate body above it than by the compact center below. The planet is therefore not best imagined as a large iron heart surrounded by a thin shell of rock. It is better imagined as a world in which the central dense region is present, but comparatively small, within an overwhelmingly hot rocky envelope. Even this picture remains uncertain at the finest level. The deepest interior of an exoplanet cannot be observed directly. Its existence is inferred from mass, radius, thermal evolution models, and the general physics of planetary differentiation. Several possibilities remain open. One is a more clearly separated metallic core, dense and compact beneath the silicate body. Another is a transition region in which the boundary between metal-rich and silicate-rich material is less sharp than it would be in a cooler, more settled terrestrial planet, under extreme temperature and pressure, with long-lived molten conditions and chemically unusual sulfur-rich material present. The center may not behave as a perfectly simple sphere of cleanly isolated metal. Sulfur complicates this deepest region further. In planetary interiors, sulfur can partition into metallic material under some conditions, meaning it can become incorporated into the core rather than remaining entirely in the silicate melt. If this occurs on L98-59d, the core may not be made of iron alone or of iron with only the small light element fractions familiar from standard terrestrial comparisons. It may include substantial sulfur or other lighter components that alter its density, melting behavior, and separation from the surrounding silicate interior. This possibility matters because it affects both the exact size of the core and the sharpness of the contrast between core and mantle. Pressure at the planet's center is immense. Under such pressure, materials take forms not seen at the surface. Density rises, atomic arrangements shift, and the behavior of melts and metals can depart from ordinary low-pressure intuition. In a cooler rocky world, the deepest interior may organize itself into a more settled layered structure over time. L98-59d remains unusual because its central region exists beneath a planet that never fully matures into that familiar cooled state. The core therefore belongs to a world whose large-scale structure remains thermally inflated and compositionally dynamic far above it. This means the exact lower limit of the molten silicate body is not yet known with complete certainty. The transition from silicate-dominated interior to metallic center may occur at different depths depending on the accepted model, the assumed sulfur content, and the bulk density estimate used. Some models imply a more compact core and a thicker silicate envelope. Others allow a somewhat larger dense region without changing the broader conclusion that the molten rocky body dominates most of the radius. The uncertainty is not a sign of failure. It is a sign that the available data constrain the planet strongly at large scales, while leaving room for several related deep interior configurations. In a sense, this is fitting for the deepest region of such a planet. The outer atmosphere is visible through filtered starlight. The surface and magma ocean are inferred through their thermal and chemical consequences. The deeper mantle is reconstructed through bulk structure and evolution models. This central core lies at the furthest edge of inference. It is the innermost region and the least directly knowable, yet even here the picture is not empty. The data support a world in which the central dense region exists beneath the molten body, remains smaller in radius than the silicate envelope above, and may itself be compositionally unusual because of the planet's sulfur-rich nature. The deepest center of L98-59d is therefore not the simplest part of the planet. It is the part where standard terrestrial expectations become faintest. There is probably a metallic core. It is probably relatively small in radial extent compared with the vast molten silicate layers above. It may contain sulfur or other light elements that make it less like the cores of the rocky planets known from the solar system. Its boundary with the surrounding interior may be present but not perfectly simple. Beneath all the sulfur-bearing air, beneath the atmosphere's heat blanket, beneath the surface melt, beneath the global magma ocean, and beneath the deep silicate mantle, the planet gathers at last into its densest hidden center. Yet even there, certainty softens. The core is inferred, bounded by physics, and partially veiled by the unusual world built around it. The picture settles inward to that last concealed region and comes to rest there. L98-59d appears to be a planet whose center survives as a compact, dense interior, but one overshadowed in scale by the immense molten envelope above. It is the deepest part of a world that never becomes ordinary. The planet's center likely exists as a relatively small metallic core, while the great body of the planet remains dominated by long-lived hot silicate material. At the innermost limit of current knowledge, that is where the new planet type finally narrows to its quietest point, a hidden core, smaller than expected, enclosed by a world of melt. The mind now rests with that concealed center and lets the planet remain whole again. Far above the dense inner region, the molten body still turns in silence around its faint red star. The sulfur-rich air remains suspended over liquid rock. Heat continues to move through the broad mantle of melt. The deep reservoir keeps its hidden chemistry. At the very middle, the compact interior stays beyond sight, held only by inference and by the steady order of physics. Nothing in this world is familiar in the ordinary terrestrial way, yet each layer follows from the last with calm consistency. Across the script, the planet has been approached from the widest setting to the deepest hidden region. The outer census of impossible worlds narrows to one compact system, one red dwarf, one close orbit, one faint transit signal, one low-density body, one sulfur-marked sky, one thick hot atmosphere, one molten surface, one global magma ocean, one deep silicate interior, one buried sulfur reservoir, and at last one small inferred center. The whole structure remains strange, but not chaotic. It is a coherent planet, simply one that does not fit the older planetary boxes built from the solar system alone. In that quiet recognition, the world becomes less a curiosity and more a reminder. Planetary nature is wider than familiar examples. A planet can keep molten rock at its surface for billions of years. It can hold sulfur deep within and feed that sulfur into a hostile sky. It can remain too light for a simple rocky body and too chemically distinct for the older labels that once seemed sufficient, it can circle a small dim star and still become a place of lasting heat. It can gather into a small dense centre while most of its volume remains in a hot expanded state. This is not a failure of order, it is a fuller expression of it. The new planet type that should not exist remains where it is, complete in its own logic, distant and untroubled by expectation. Its air, melt, mantle, and hidden core continue in slow relation to one another. The measurements from far away remain delicate, and some details are still uncertain, yet enough is known for the planet to take its place among the real worlds of the galaxy. It does not need to resemble Earth or Neptune or any earlier category to be understood. It only needs to be followed patiently from the outside inward, until the final hidden centre is reached, and the rest falls still around it.